gaseous emissions from livestock farm and manure management. My name is Laia Llenas. I'm the Deputy Director of Beta Technological Center, and I'm also part of ESNI management team. So I'm here together with my colleague Nagore Guerra, who is here connected. The two of us are coordinating the working group on technologies for nutrient recovery of the ESNI community. Okay, so ESNI Community counts with the participation of 20 projects working together and joining efforts to broaden the impact of research and innovation in the field of sustainable nutrient management. ESNI counts with 4 different working groups that are working on identifying main research and innovation knowledge gaps to better understand what is going on and what is needed in the future research activities. So in this regard, we did an exercise last year to identify different topics that could be of interest and that had to be tackled in future research. So in this regard, one of the hot topics identified in this exercise that the ESNI community did last year were the polluting gaseous emissions at farm level. And that's why we are here today as a continuation of what we did last week. So last week, we had the first session of this webinar series, where we were able to explore the development and application of harmonized methodologies for measuring gaseous emissions. We addressed current monitoring challenges and discussed the potential for standardization, an essential step towards improving data consistency and comparability across different farming systems and regions. We had 2 very nice presentations, one from ILBO and the other from CITA, the Technological Center Research of Aragon. And I would like to thank again Anne, Noemi, and Adelaida for their nice presentations. I think that they were very interesting and we learned a lot from them. And today we have the second session of this webinar series, and today we will shift the focus to the status of best available techniques, BATs, and reference documents, BREFs, for intensive livestock farming. For that, we are counting with the participation of the Joint Research Center, and we will also have 3 different presentations that will showcase different innovative approaches to emission control and mitigation, emphasizing real-world application that can contribute to the acceptance and implementation of the best available techniques. So in this regard, we hope that the presentations that we will have today can be of your interest. So we invite you to be engaged in the discussions, ask questions to our speakers, and share insights as we explore solutions that can drive meaningful progress in emissions management. Feel free to use the chat to put any comments that you may have. And also after each of the presentations, we will open the floor for questions. So I hope that you can be active, asking to our speakers your questions and share with us your concerns. So I think that with that, we can start with our first presentations of today. The presentation is titled Best Available Techniques for Livestock Sectors. Will be done for Diogo Moniz. Diogo works at the European Bureau for Research on Industrial Transformation and Emissions, EU-BRITE, at the Joint Research Center in Seville. He's currently working in the team responsible for developing the uniform conditions for operating rules for livestock within the frame of the Industrial and Livestock Breeding Emissions Directive. So Diogo, the floor is yours. So let me know when you want that I pass to the next slide.
Perfect. Thank you. Thank you very much, Maya. Thanks very much for the invitation. Very happy to be here. Good afternoon, everyone. And indeed, as Maya mentioned today, I would like to talk to you about the best available techniques for emissions and prevention control in the livestock sector, but only referring to pigs and poultry, since this is the mandate that we have for our work. I'm also joined today by Panos and Francesco. They are following online. We are the team working on this specific project. So yeah, please, for any questions or comments in the future, feel free to reach out to us. A bit on the overview of the presentation. Indeed, it would be great if I could summarize all the best available techniques that are currently in force by the work that has been previously done on this sector. However, the document is quite big, is 850 pages long. Some of you might be familiar with it. Of course, the more technical and specific chapter on the conclusion on the best available techniques, it's much smaller. But anyway, since it's hard to do all of that in 15-20 minutes, we bring you, well, a little bit of an overview of the process that we use to, well, produce these documents and make this analysis. We also bring you an example of what's the outcome of this analysis. And yeah, a little bit on the work done in the past and the work done that will be done now in the future. So very quickly, well, it's the EU policy framework that basically governs the work that we do at EU BREFs. The process that we use to make all of this happen, which is called the Seville process. Then we'll go briefly on the collection of information for candidate best available techniques. The best available techniques that are currently in force for the intensive rearing of poultry and pigs. I would also like to take just a brief moment to talk to you about the Innovation Center for Industrial Transformation and Emissions Insight, which is a little bit the new baby of EU BREFs. And yeah, we'll leave you with some takeaway points. So, Lai, if you don't mind going to the next slide. Thanks. So, okay, starting from the very beginning, my team at JRC, well, operates under the Industrial and Livestock Rearing Emissions Directive, or ID 2.0 for short. And in general terms, well, our team coordinates the exchange of information that underpins the drawing up, review, and update of the best available techniques reference documents, or BREFs for short. You see, we call it ID 2.0 because the previous directive has actually been amended. And the new version has entered in force on the 4th of August 2024. The rules governing the information exchange, the data collection, and the procedures to draw up the BREFs are embedded into the law under the Commission implementing decision. And this decision serves as a sort of a BREF guidance that in turn provides all the information on what is commonly referred to the Seville process that I mentioned before. So if we could move to the next slide, please. This is a little bit what the new ID 2.0 consists of, and it has a few new elements to it. It has this new forward-looking and innovative approach, which is materialized in insight that I mentioned before, and I'll explain a little bit better down the presentation. The updated rules will make emission limits values stricter. It will require electronic permitting by 2035. It aims to reduce the administrative costs and tighten the conditions on granting derogations. This is more a curiosity for the topic of the presentation here, but the ID indeed 2.0 recognized for the first time the EU environmental law the right for people to seek compensation for damage their health caused by illegal pollution. And more specific on the sector that we are today talking about, the coverage of these intense pig and poultry farms will actually be increased based on the previous version of the ID. It excludes organic pig farming. And well, this is done with the aim of reducing nitrogen pollution, most of all. These farms will be also subject to lighter permitting and hopefully allow for a simplified registration option as well, according to the willingness of the member states. So next slide, please. Oh, yeah. Thanks. Just to very quickly, I would like to show you some representations of some numbers put together by the European Environmental Agency, or EEA for short. This is regarding, well, the magnitude of some general sectors emitting specific pollutants. So EEA's report is actually quite detailed. I just chose these three as reference. And well, for instance, the non-methane volatile organic compounds in agriculture, well, would be mostly associated with waste incineration from arable crops or horticulture. So it's not directly related with livestock rearing. However, ammonia and nitrous oxides are directly related with the livestock rearing activities. And well, as you all know, they are associated with important environmental issues. Can we move to the next slide, please? Still on the EEA numbers, this graph very simply represents, well, some of the results of the implementation of the IID along the years. And well, it's just a way to show that it's indeed possible to reduce emissions without destroying the European economic fabric. Next slide, please. Before actually delving into the Sevilla process itself, I would just like to emphasize that the IED is a permitting directive, and it permits based on the best available techniques conclusions of, well, the bad conclusions for short, as we call them. And these bad conclusions, well, they are a specific and dedicated chapter of the BREFs, which is this main document that we produce in the end of the Sevilla process. And the bad conclusions, well, it contains a lot of information on the assess of, well, it starts with a descriptive text of the technique. It informs about its applicability, the emission levels associated with these techniques, or the environmental performance levels associated with these techniques if we are talking about resource efficiency or water consumption or energy efficiency. It also contains it also has content on the environmental management systems, and including benchmarks, and it also contains information on associated monitoring. So if we could go to the next slide. So the Sevilla process itself, well, it's here is a very also simplified descriptive process that we go through. After the selection of the industrial sectoral activity, well, there's the activation or reactivation of the technical working group. Well, this technical working group is a group of experts that is composed by, well, all member states and the respective relevant ministries. It's also, the technical working group is also composed by representatives of the industry, in this case, farmers, but not only farmers. We also have feed manufacturers, and it also has the presence of environmental NGOs. So this is quite a big group. Its number can vary, but it's usually in the order of the hundreds of people. And well, it's the difference between activation and reactivation. It's simply if the process is being reviewed from work done in the past, or if it's a new group formed to tackle the construction of a BREF in a new industrial sector activity. So after the group is formalized, we go through the front-loading exercise, where we basically address the main environmental issues that we want to approach in this discussion. We ask specific questions on the more technical side of each issues, how we should go about them, what might be the data available in different member states. And based on the feedback that we get from the working group in this front-loading exercise, we produce a proposal. Well, we do an assessment and produce a proposal that we present at the kickoff meeting in Sevilla, where we all meet in the same room for between 3 and 5 days, and we discuss all the issues that were covered in the front-loading exercise and additional issues that the working group would like to discuss. And all together, we discuss and come together with a version of the proposal where everyone is happy with and that is feasible, and that can basically lay the ground for the collection of information and then the assessment of the information and the data that we collect. After this collection of and assessment of data, we draw up the first draft. I went by these 3 squares really quickly, but this is perhaps what takes the longest in the Sevilla process. It can be between 1 year or 3 years. It depends on the type of document that we are producing. During this period, we also encourage site visits that are usually organized either by member states or members of industry, but it usually comes, or it definitely comes from the working group to organize these site visits. And we might have also technical workshops on specific types of techniques or specific environmental issues that need further discussing. Or that there's a particular member of the working group who holds an expertise and would like to share with the group. So all of these are organized throughout this period. So when we actually draft the first version of the BREF, we submitted, of course, for round of comments, and then there's a final meeting in Sevilla, and again, we all come together to discuss and to make sure that everyone is happy with what would be the final draft and publication of the BREF. Next slide, please. Yeah, thanks. So how do we collect all this information on the techniques? Well, we use this 10 heading templates that is described here in the slide, and also a quite simplistic form. As you can see, it requires some effort from whomever is submitting the information. And it also requires some examples on existing plans, so things that are actually working. So this is for available techniques, emphasizing the available. And this brings me, well, there was and there still is a chapter reserved in the BREFs for emerging techniques. And in this chapter, well, we collect information on techniques that could outperform existing best available techniques. However, we do not do a deep analysis for these emerging techniques, technically wise, collecting data and so on. So this brings us to one important comment that was made on the previous version of the IAD, which was indeed its lack of forward thinking towards the development of innovative techniques. Next slide, please. So this is the reason of insight, which is the new element of IAD 2.0 for tackling the industrial transformation. It indeed adds to the Sevilla process and has this forward-looking mechanism, which is definitely a necessity for the evolution of the best available technique concept as a whole. Insight will become a central point of reference for identifying and evaluating the environmental performance of innovative techniques. And well, the platform is currently online, so and it's online and running. So we invite everyone to visit the platform and to take a look at the structure that the team came up with for submitting information on innovative techniques. Next slide, please. Yeah, perfect. So now a little bit about the existing work on the best available techniques for intensive rearing of poultry and pigs. There is a BREF that has been published some time ago. The IRPP, Intensive Rearing of Poultry and Pigs Best Available Techniques Conclusions, was published in the 15th of February 2017. And in it, well, there's 34 bad conclusions covering generally nutritional management, animal rearing, and manure management. On nutritional management, we have 7 BAT-associated nitrogen excreted levels and 6 BAT-associated phosphorus excreted levels for different animal categories of both pigs and poultry. And on manure management, we have the 1 BAT-associated time delay between manure land spreading and the incorporation in the soil. Apart from this, well, the IRPP also includes conclusions to reduce emissions on dust, odor, and noise, and also conclusions on the efficient use of water and energy. So perfect. This is actually an example of the outcome of the exercise for ammonia emissions. And so after collecting the information on all the techniques and agreeing with the working group about the animal categorization and collecting all the available data, we come to a certain BAT-associated environmental limits, or BAT-AEL for short. Now, please keep in mind that BAT conclusions are secondary legislation, and they serve as basis for permitting. So immediately you might spot a few hurdles to use this table in the most effective way, because well, there are not a lot of animal categories, and some of the ranges, well, they are more than a tenfold difference between the inferior limit and the upper limit, and it also has quite a lot of nodes. Well, there are good reasons for these characteristics that I just explained. It's because indeed, well, it was, to begin with, the first time the team was going about this sector, and then it's true that there's a really big diversity in the sector, not only in, well, the type of installations and farms that we have, but also even the different biogeographical regions of Europe. There's different cultures in the rearing of poultry and pigs in different regions, let alone countries. So it's hard to come about with a common vision for it all. If we could go to the next slide, please. So actually, poultry and pigs rearing is also addressed under the new framework. So what does the IED 2.0 tells us about it? Well, it has a dedicated chapter it's called Special Provisions for Rearing of Poultry and Pigs. And in it, we can find a lot of information. There are new thresholds for farms, and this time they are defined in livestock units. So what this meant is that now we have a higher coverage of farms. We went from 23,000 more or less to 38,000 more or less. There's also an increased implementation flexibility. So there are general binding rules, there are permits, there is the possibility to do just the registration of the installations, this according to the preference of the member state. And yeah, there's the detailed technical requirements based on the Uniform Conditions for Operating Rules on Livestock, or UCOL for short, to be published within 24 months after the entry into force of the IED 2.0. So this is the project that me, Panos, and Francesco are now currently working on. And 24 months after the entry into force of the IED 2.0 means the legislation needs to be ready for adoption in September 2026. If we could go to the next slide, Laia, please. Yeah, thanks. So this is indeed what's next is UCOL. We have had the kickoff meeting in Sevilla. It's quite fresh, 3 weeks ago. We are still digesting all the information that we got and are now preparing well how we would go about evidence collection and information collection. We'll, of course, this is well, what's expected of us in general terms is to go about the emission and environmental performance level of the installations, to address monitoring techniques, to address cross-media effects, economic and technical viability, the best available techniques, of course, and the emerging techniques. So this is what's expected to be in the document. If you could go to the next slide, please. More specifically, we after the information and data collection, we want to address particular environmental issues. Regarding emissions, we would go obviously address ammonia emissions, and we would also address methane emissions with certain twists. Of course, it's also the first time methane is being addressed, and as you notice, cattle is not is out of the scope of this process, so it has some notes to it. Would go through dust and other emissions as well, total nitrogen and total phosphorus excreted. These are not new, also present in the IRPP. Then regarding environmental performance, we'll address water consumption and energy efficiency, and we'll also delve into the monitoring methodologies. There's plenty of challenges ahead of us. We have a very strict timeline that requires quite tailor-made information and data collection. So this will not follow the traditional BREF procedures in that aspect. The animal categorization is indeed very important to derive shorter but AEL ranges, or limited to a single value. This was very much stressed at our meeting and information exchange. But on the other hand, there's also the issue of data availability across the member states. So there's definitely a compromise to be found there. There's an ongoing discussion about the standardization of emission factors for the intensive rearing of poultry and pigs across all Europe. Also ongoing discussion on monitoring techniques for ammonia emissions. And another interesting, important outcome of our information exchange was that animal welfare will be an overarching consideration throughout the analysis, meaning basically that all environmental issues are addressed in a way that guarantees animal welfare standards. So this is a little bit the summarization, maybe just to leave you with a few takeaway points of the Sevilla process and of what we do at EU Bright. Well, a best available techniques-based approach that have definitely proven to be effective in Europe and will enhance under the new framework. Livestock rearing is a crucial economic sector in the EU with the great potential for sustainability practices. The challenges in collecting data and evidence reside mainly in the diversity of the sector and the quality of data, and also on the monitoring methodologies available. And that science and evidence are at the heart of the legislation to make sure that we have a participatory approach, data-based and transparent process. So that concludes my presentation. Thank you very much. If there are any questions, either me or Francesco and Panos are also here. Let us know. Thank you.
Thank you very much, Diogo, for the clear presentation. I think that, many of us have been able to understand very well, all the process that you are doing, but I'm also sure that there should be some remaining questions or doubts on how we have to proceed, or what do you need. So let's see if someone has questions from the audience. So in the chat, I cannot see any questions yet. Come on, don't be shy.
It's also okay if you are shy. You can always drop us a message.
Yes, you can write the question. It's easy.
Exactly. Just drop us a message and feel free to contact. Please go and check the Insight platform. It's It's also quite new, so we are looking for techniques, looking for people who want to submit information. So yeah, it's also there for you.
Yes, no. So I think that, well, at least for me, it was very clear. So, and it's highly appreciated that you wanted to participate in this webinar. So I think it has been very useful to be aware on this ongoing process. Maybe after all the presentations, we can open again the floor for questions, or if you change your mind, someone wants to change their mind and put some questions in the chat, feel free to do that, and we can come back to further discussion after the next presentations. So
Thanks.
Thank you very much, Diogo, again for being here today. So I will move then to our next speaker. He's Elio. Let me check the CV. He's Elio Dinuccio. Elio has a PhD in agricultural and environmental engineering. He's associate professor at the Department of Agriculture, Forest and Food Sciences in the University of Turin. And he has expertise in agricultural engineering with special regards to mineral and organic fertilizers spreaders, manure and organic waste management concerning water, soil and atmospheric pollution, nutrients and energy valorization. So Elio will do a presentation titled Acidification and Nitrification Inhibitors as Strategies for Emission Reduction in Livestock Farms. And I think, Elio, you will share your screen, right?
Yes.
Okay,
can you hear me?
Yes, we can hear you. So if you want to try to share the presentation.
Can you see the presentation?
Yes, it's working well.
So, great.
Perfect, thank you.
Thank you. So, thank you very much, Naya, for your presentation. And I'm going to provide you some insight on two specific mitigation strategies that are nitrification inhibitors and manure acidification, according to our research experience. But before going into the detail, I would like to give you just a short overview of the Italian livestock situation. So, at the moment, it's estimated that livestock manure could contribute to around 75% of the total agricultural greenhouse gas emissions from agriculture, and around 6.3% of the total human-induced greenhouse gas emissions, based on the amount of emission of carbon dioxide emission equivalents estimated that are equivalent to at around 25.5 million of tons per year. Nitrous oxide alone, it's estimated to contribute to around 50% of the agricultural sector. But livestock manure is also an important source of ammonia emissions. So ammonia is of great concern because it's a pollutant, but it's also related to fine secondary particulate matter formation. So in this regard, the regions of the Po Valley in the north of Italy are, in general, this area are most of the areas where these pollutants are more concentrated in the air because of livestock sector that is mainly concentrated in these regions, but also because of the specific environmental conditions and also for the presence of the Alps that reduce the movement in the air, and so the concentration of ammonia and especially of PM is very high. In this situation, during the last years, some restrictive legislative legislative acts have been implemented in order to reduce these emissions and to also avoid secondary fine PM formation. According to the best available techniques, the main strategies that are supported to avoid to reduce such emissions are, of course, anaerobic digestion for both solid and liquid manure. It's well known the role of anaerobic digestion in reducing greenhouse gas emissions, but also covering the storage facilities and to adopt strategies like slurry injection or bed spreading with slurry. And in the case of solid manure, it's important to incorporate the manure immediately after the application. But of course, this strategy to be effectively implemented need to be better and well investigated, because of course we have to avoid trade-offs, in particular pollution swappings. But we already know that most of these strategies can produce pollution swapping. For example, in the case of slurry injection, it's the best strategies to reduce ammonia emissions. We can reduce up to 95% ammonia emissions, but compared to traditional splash plate. But it's well known that there is some problem related to the increase in PM emissions, but also there is the opportunity to produce and increase nitrous oxide emissions. In the case of surface band spreading, also of course, band spreading potentially reduce up to 50% ammonia emissions compared to the broadcaster splash plate system, but especially in Mediterranean regions, ammonia emissions can still be pretty high because of climatic conditions, especially in some situation of high temperature and high wind speed. We measure ammonia emissions that are comparable to a splash plate application. And also, this strategy can affect nitrous oxide emissions. What are the drivers? What are the mechanisms and the factors affecting nitrous oxide emissions are well known. It's the main driving factors are nitrate availability, the environmental and soil conditions, and basically nitrous oxide is the byproduct of nitrification and denitrification mechanisms due to oxidation and reduction conditions. So, in this context, within the Clean Med Farm project, that it's a life project that has been already mentioned the last week by the colleague from CITA, we are testing and demonstrating the different technical solutions in order to, in general, to improve the energy and environmental efficiency of livestock cattle systems connected to biogas plants, so that produce digestate. And the idea, the concept is of this scheme is to to promote and test different solutions at the different stage of manure management, and by considering the whole flow system. So we are testing solution in the building, in the storage facility. We are testing innovative technical solutions to improve the efficiency of energy conversion for biogas production, and in particular for digestate application, we are considering bed spreading slurry injection in combination with nitrification inhibitors and the acidification with sulfuric acid. Why nitrification inhibitors? So nitrification inhibitors are additives that can help to reduce nitrous oxide emissions, but also to increase the ammonium nitrogen available for plant by slowing or reducing or inhibit the first stage of the nitrification process. So by slowing this reaction, there is more nitrogen in ammonium form, and then it's reduced the possibility, probability to produce nitrous oxide as a byproduct of this reaction. There are different additives and molecules that are available also in the market, and in particular we are testing the efficiency and the possibility of using the nitripyrin-based nitrification inhibitor that is provided by Corteva, that is a company that is supporting our project. We tested the application of these additives in combination with two slurry types on maize ryegrass rotation. So the idea of all the strategies we are testing is to be tested and demonstrated under real water condition. So we selected a representative livestock farm in our region, in Piedmont region of the north of Italy, and assessed the effect of this inhibitor on nitrous oxide emissions, ammonia emissions, and the biomass yield by considering these two maize ryegrass crops rotation. Here you can see the general experimental design. We selected a field. It's characterized with loam soil. We tested two slurry types, cattle slurry and cattle digestate, in combination with the two doses, according to the dosage suggested by the provider. In combination, of course, with slurry injection before seeding at an application rate of 260 kilograms of nitrogen. That is the typical application rate used for maize, for the crops. And here you can see the description of the methodology we used to assess gaseous emissions. For nitrous oxide, we used the closed static chamber technique, and for ammonia, PLS micrometeorological method combined with alpha samples and 3D anemometers. These methodologies have been already in detail described by the colleagues from CITA the last week. Here you can see the results from both maize and ryegrass cultivation. How you can see nitrous oxide emissions were related mainly to environmental conditions, especially rain and rain events. But generally, nitrous oxide emissions were higher from the non-treated manure as compared with the treated slurry. In general, nitrous oxide emissions were reduced on average around, let's say, 50%. Yes, 47% for maize and 40% in the case of ryegrass. Ryegrass is cultivated in autumn-winter conditions, so the nitrous oxide emissions were generally lower during this the cultivation of these crop compared to maize. Also, you can see, okay, in summertime with maize, the cattle was the main emitting source, but on the contrary, in winter's time, nitrosate showed the higher nitrous oxide emissions. But in generally, on average, nitrous oxide emissions were lower than 1% of the total nitrogen applied. And also, here you can see the effect of the nitrification inhibitor on the biomass yield. And on average, with maize, the additive increased by 11% biomass yield, and for ryegrass increase by 6%. This okay, the effect were significant in the case the positive effect on were significant in the case of nitrous oxide emissions, but nevertheless, in the case of biomass yield, the effect were not statistical. Statistically evident. So moving to manure acidification. Manure acidification is also a well-known mitigation strategy. Is mainly applied to reduce ammonia emissions. Is widely used in Denmark when is applied by using strong acid like sulfuric acid, but also by acidification in some cases could be an interesting option. According to literature review, manure acidification with sulfuric acid has the potential to reduce up to 70% of ammonia emissions, but also the potential to reduce methane, because by reducing the pH, is possible to inhibit also the activities of methane archaea that are responsible of the production and emissions of methane, but can also have an effect on nitrous oxide emissions. The principle of manure acidification in reducing ammonia emissions is also well known. Basically, by by lowering pH to a target level of around 5.5, ammonia emissions is virtually zero because all the nitrogen is in the ammonium soluble form. But the use of strong acid, like sulfuric acid, presents some challenges, some problems, because it's a hazard for, it's dangerous for humans, of course, but during storage there is also the problem of foam formation. There is the buffer capacity of the system that tended to increase again the pH. And another problem is related to the fact that this strategy cannot be used for the solid manure. Of course, also the cost is an important issue to be addressed. We, in order to overcome this problem for during storage, we found elemental sulfur as a good option to be used to reduce, to acidify the manure, especially the solid manure, instead of strong acid like sulfuric acid. Within the Life Agri-Gloves project, we developed a prototype to automatically dose elemental sulfur to a rate ranging from 1 to 5 kilograms of sulfur per cubic meter of raw slurry before mechanical separation, in order to have a liquid and solid acidified fraction. So, according to our experience, by using these strategies, it's possible to reduce up to 55% ammonia emissions during storage of the liquid slurry as compared to non-acidified manure, and to reduce up to 60% ammonia emissions during storage of both the solid and liquid acidified fraction. So it's a very interesting option for manure storage. Within the Life Cleanment farm, we are focusing on slurry acidification with sulfuric acid before slurry band spreading. We perform some preliminary investigation in the lab by using different dosage of sulfuric acid, and perform emission trials using mesocols with soil and the slurry applied at a rate of 170 kilograms of nitrogen per hectare. We measure emissions by using the K-pulse analyzer, that is a laser photoacoustic analyzer, in combination with a ventilated chamber. Here you can see the results of how you can see with both the kettle and digestate. By adding sulfuric acid, we significantly reduce the pH up to 5.8 in the case of the higher dosages. Acidification, slurry acidification, was able to significantly reduce ammonia emissions after application up to 44%, but had not effect on nitrous oxide emissions. So that means that if we want to mitigate also these important issues, we have to combine the acidification with other mitigation options, like, for example, nitrification inhibitors. Now we are moving to the field based on the after the first preliminary results in the lab. We are testing a prototype for direct acidification of digestate before application on grass. For that, we are collaborating with Volgesang, that is a leader company on this field. And the idea is to combine the acidification with the umbilical system. That is an interesting emerging option, especially in our country, due to the benefit related to the reduction of the costs, soil compaction, and so on. So here you can see the general overview of the prototype, the main components. The prototype has been already developed by Volgesang, and we are going to test this solution in 1 month in a real field condition. So, in conclusion, according to our experience, acidification and nitrification inhibitors are promising and effective options for reducing both ammonia emissions in the case of acidification, but also greenhouse gas emissions in the case of nitrification inhibitors, but also is an opportunity to improve the nutrients efficiency of the manure. But of course, there are some challenges to be considered. We have to. One is the scaling up implementation. So we have to adapt these strategies to different farm systems and conditions. There is a lack of information about the long-term effects of these strategies in terms of soil health, microbial dynamics, and general sustainability. The economic feasibility is another important point to be addressed, but also it's another important point is to be underlined is the need of public and policy support. So especially for example, for the acidification, it's very important it's very important to have the public support in order to be widely spread. Because at the moment there are very few companies that provide these technologies, and also the technologies are the investment costs are very high. So it's very important that public support in order to make these strategies available at feasible costs for the farmers. So thank you very much for your attention.
Thank you very much, Elio. Very nice presentation, many information, shared results, and also I liked a lot this last slide, as a wrap up, and also telling what it's needed to be able to implement these strategies. So thanks a lot for sharing this with us. Any questions for Elio? You can write them in the chat, or please raise your hand if you have any questions. No? Okay, so people is still shy, I see. So, well, so I think that then we can wait and let's see if at the end someone is willing to ask something. Thanks again, Elio,
Thank you.
for your presentation. I will share again now my screen. Can you see my screen? Yes.
Yes.
Perfect. So we will move to the third presentation for today. So our next speaker is María Cruz Garcia González. María Cruz is a full professor at the University of Valladolid. She's specialized in organic waste treatment and nutrient recycling with an important research activity of great scientific importance, resulting in more than 70 international scientific articles and book chapters. Maria has an active participation in different specialized courses, workshops, and more than 80 international and national conferences. And she has experience at different international and national research projects, being coordinator of 6 competitive national projects and participating in 6 European projects. So Maria will be presenting the evolution of an ammonia capture technology to reach BAT from TRL1 to TRL7. So if it's fine, Maria, I will continue sharing my screen. So I will pass the slides.
Yes, please.
Okay. So the floor is yours, Maria.
Thank you so much. Thank you, Laia, and thank you, Nagore, for inviting me to this workshop. And as you said, my talk is addressed to explain my experience working with the membrane technology to capture ammonia from manure and how to bring the technology from TRL1 to TRL7. First, next one, please. First of all, I'm going to introduce the team of the University of Valladolid, which is made up of 2 teachers, myself and Dr. Mercedes Sanchez, a Ramón y Cajal researcher, that is Beatriz, 1 postdoc, that is Laura, and 2 predocs that are Paula, Elisa, and a technician, that is Ernesto. Next one, please. Thank you. We have been working with organic waste for many years, more than 20 years. So we have participated in different projects and developed many projects. Some of them address to manage and treat liquid and solid manure. We have been working with anaerobic digestion, with composting, with land application, and also with nitrification and denitrification treatments. So in the last projects, we have been working with membranes, specifically gas permeable membranes, to reduce ammonia emissions from the animal houses and also from pig manure. Next one, please. Okay. We have developed a technology that is based in the use of gas permeable membranes that are able to let the ammonia permeate through the membrane, but not other compounds of manure can permeate through it, as for example soluble COD or for example solids. This ammonia is captured by a stripping solution that is a diluted acid that is on the other side of the membrane, as you can see here in this picture. So the driving force for the ammonia transfer is a difference in concentration of ammonia in both sides of the membrane. The process is carried out at atmospheric pressure and at ambient temperature. And once the ammonia is in the acidic solution, it combines with the protons of the acids to form a non-volatile salt. The membrane can capture also, no, not yet. The membrane can capture ammonia from manure, from digestates, and also from the air. And we obtain an ammonium salt that is a fertilizer. We start working at the lab scale and TRL1, and now we are trying to develop a commercial device. So we are working at a TRL of 8, 9. Next one, please. Okay. My first contact with the membrane was with this technology was during a research visit with Dr. Matthias Vanotti from the USDA from Florence, USA. He was working with the membrane and he did the first studies to see its behavior and how the membrane was able to capture ammonia from manure. I bring some membrane to Spain and started working with in the lab, doing some experiments with manure, with digestate, and also the Doctora Mercedes Sanchez in 2014 was working with a flat membrane to capture ammonia, but she was working with to capture ammonia from the air. Next one, please. In Spain, I work with to optimize the parameters, some parameters of the technology, as for example, how to improve the aeration to increase the pH, to improve ammonia volatilization. We also worked with membranes life, and also with different type of acid solutions to see what was more efficient with capturing ammonia. Therefore, developing more knowledge meant to reach a TRL 3 and 4. Next one, please. Okay. As a result of those experiments in the lab, we published some papers and some bibliography, and apply for a patent of the technology that we got last year. Next one. Thanks to the background and the publications we gained from the lab work, we were able to apply for some funding to develop a prototype capable of working at farm scale. So we got the live ammonia trapping. That it was a project because it has already finished. It was a 4 years project. We got a funding of 1.7 million euros. And here you have the partners. The partners were the University of Valladolid. We were working developing an air prototype because during this project we developed two types of prototypes. One prototype that was developed by us. It was called air prototype because we capture the ammonia from the air. And the Funge was the administrative coordinator, and Itacil was working in what we call the liquid prototype. So they were developing the prototype to capture the ammonia from the manure and from digestate. The Porcil was pig farm, Avicolacea was a lion hens farm, and Enusa was a company that had a biogas plant. And Inderen was our technology partner. They help us. They were the engineering that helped us to develop the prototype. So with this project, we were able to bring the technology from the TRL4 to a TRL7. Next one, please. In this project, we were working capturing ammonia from pig manure and from pig and lion hens houses, from the houses of the pigs and the lion hens, and also from two types of treatments called anaerobic digestion in a biogas plant and composting, as both processes also can emit ammonia to the air. During the year 2018, both prototypes worked in the pig farm in Palencia. And then in 2019, the liquid prototype was transported to Salamanca to work in the biogas plant. And the air prototype was transported to Soria to work in the lion hens farm. And also in this lion hens, we had a composter. Next one, please. The first task of the project was to design and construct the prototypes. Here you can see what we call air prototype. This is the main structure of the prototype. Both prototypes, the air and liquid, had similar components. They had an acid tank with the stripping solution was used to recover ammonia. A metallic structure where the membrane panels were arranged. Also, they have pH and temperature proofs to control these parameters. Pumps, air blower, a control panel to display the system control parameters, and pipes and so on. In the next slide, yes, okay. Here you can see the pictures of the air prototype. This is the main structure of the prototype where the panels with the membranes were arranged. Here below is the acid tank, where the acid tank was provided by all the system to continuously recirculate the acid to capture the ammonia. And here you can see in this picture, you can see the arrangement of the panels. And here there is one panel with the membranes. And here you can see a picture of the prototype inside the house of the pigs. You can see the pigs at the back. Next one. This is the Lion Hens farm in Soria. This was a free-range farm. And that was a problem because these small doors that you can see here were open almost all the day, during all the day. And as they were opened, they allowed to the ammonia go out to inside the barn. So this reduced the amount and the concentration of the ammonia inside the building, and the capture of ammonia was less than we expected. Here you have the air prototype here connected with a pipe to inside the houses. Okay, inside the house, sorry, because this is just a house where the lion hens were living. And here you can see the air inlet pipe from inside the house to the prototype. It was located above the hens' manure to absorb as much ammonia as possible and transport it to the prototype. Next one, please. Okay, here you can see the composter. So when we finish to test the ammonia capture from the houses, we connected the prototype to the composter to capture ammonia from it. We did different experiments with different setups, with two different setups. I'm going to explain you later on the setups. But here you can see the composter and here the air prototype connected, in that case, with a lion hen's house. And here you can see in this picture the membrane layout inside the composter. Next one, please. Okay, next one, because this is an animated slide, so I need one more. Okay, thank you. Okay, this is the liquid prototype, and it was made up of a 5 cubic meter manure tank where the membrane panels were arranged, as you can see here in these pictures. This is the tank, and these are the panels. You can see here one of the panels with a membrane arrangement. And it also had an acidic tank, that is this one, the green one, pumps, an air blower, and a control panel where when we can see the pH and the air blower function. The liquid prototype was located in a container. Next one, please. Next slide. Okay, you can see here the prototype, the liquid prototype inside the container, because this container allows us to transport the prototype from the farm to the biogas plant. So here in this picture, you can see the whole liquid prototype. This is the 5 cubic meters tank. with the membranes and the panels with the membranes inside the tank. The membranes in that case were submerged in the manure or in the digestate, depending on we were working with. And this is the acid tank, and here are the pipes that provide the acid to the membranes, and the acid was continuously recirculating through the membranes. Here we have an air blower. We need the air blower to increase the pH of the manure and the digestate, because that aeration can increase the pH from 7 or 7.5 to 8.5. So that way we allow this air and the increase of the pH allows the equilibrium ammonia-ammonium to shift towards ammonia. So we got more ammonia concentration in the manure, and it increased the efficiency of the membranes to capture that ammonia. And here you can see some fixing works. Here is this is Beatriz, and this is myself working, fixing some leakage of the membrane. Next one, please. Here I'm going to show you brief results from the prototypes, just some brief results. This graph shows the evolution of the tan captured by the membranes. It can be seen that it was higher in the pig's farm than in the lion hens farm, as the ammonia concentration was higher in the pigs' houses because of the management of the lion hens in the lion hens farm. And the capture was also higher during the winter than during the summer, because of the ventilation of the houses. In summer, there are more ventilation in the houses, so the ammonia concentration decreased inside, and the recovery by the air prototype was less. Next one, please. Okay, here are some results of the composter. With the composter, we did two different assays. In system 1 configuration consisted of placing the membrane on the lid of the composter, as you can see here in this picture, in the first picture, and this resulted in a much more efficient ammonia capture than in the second setup. This one consisted of extracting the air from the ammonia-laden composter and directing it through a pipe to the prototype. You can see here the composter, and this is the pipe that transported the ammonia, the air inside the composter to the air prototype. So this second setup was less efficient than the first one. So we got almost in system 1 with system 1 we achieved a recovery rate, a tan recovery rate of almost 7 grams of tan per square meter of membrane and per day, and it was more efficient, as I say, that the second setup, as you can see. Next one, please. Thank you. Here are some results of the prototype, of the liquid prototype. And in that case, the recovery was higher in the slurry than in manure, in pig manure, with a 69% of recovery, than in digestate that we achieve a 44% of recovery. The highest tan recovery rate was also achieved in the slurry than in digestate, but the numbers are very similar. We achieve 36.6 grams of tan per square meter per day in the digestate, and 38 in the slurry. And regarding the concentration of the nitrogen in the stripping solution, we achieve a maximum of 3% of nitrogen content in that solution. We also had we also did life cycle assessment of the 2 prototypes. And we got, in the case of the liquid prototype, we estimate a cost of 2.07 euros per kilogram of nitrogen recovered. This is the cost of the technology. And this is estimated for a farm with 2,800 pigs. This is just an estimation done with the life cycle assessment, as I said. Next one, please. Okay. Thanks to the project, to the ammonia trapping project, we obtained enough data to be able to request that technology to be a BAT in 2020. We produce some bibliography, some papers that you can see them if you look for them. And with all this information, as I said, we request the technology to be a BAT in 2020. Next one, please. And in February of this year, we sent a second document to our ministry. And in this case, we have requested for 2 types of BATs, one for reducing ammonia from the storage tanks, that is related to the liquid prototype, and the other from the animal houses that is related to the air prototype. So these documents, all this documentation that we have sent to our ministry are supported by all the scientific data that we have obtained in these on-farm studies. And also we have applied for the European patents, and it has been approved last November of last year. Next one, please. Okay, so I just want to say that to apply for a BAT is essential to provide sufficient data that demonstrates the technology is effective. So we achieve this data just working with the prototypes. Here in this slide, you can see the BATs where the membrane technology could reduce ammonia emissions. These BATs are BAT number 30, 31, and 32. That are addressed to abate ammonia emissions from the pig houses, the laying hens, and the chicken houses, and are related to our liquid prototypes. And the BAT 16 and 70 that address to abate ammonia emissions from manure storage and ponds, and these are related to our liquid manure prototype. Next one, please. Okay, after the ammonia trapping project, we have applied for more funding to bring the technology to a TRL 9, and we got the Green Ammonia Project, Live Green Ammonia Project, that is also a 4 years project with a funding of 2.5 million euros. And here you have the partners. The partners are the University of Valladolid. We are working to improve the air prototype and to bring this prototype to new commercial models that can be launched to the market. The Funge was the administrative coordinator. Itasil is working improving the liquid prototype. And Agropor and Agrocesa are 2 pig farms where the prototypes are working. And Quinta do Vale Junco is a chickens farm that is our Portuguese partner. So in this project, the goal of this project is to develop commercial models based on our experience with the previous project, with the ammonia trapping project. And as a secondary objectives, we have to obtain an organic origin fertilizer soil that is a renewed product, and the recognition of the technology as a BAT. So by the end of this project, when we finish this project, we expect to launch these new commercial models to the market in a TRL9. Next one, please. And just to finish my presentation, just want to underline the improvements of the green ammonia project compared to the ammonia trapping project. These improvements are main a better design of the membrane layout to be more efficient, to obtain commercial models more ergonomic and autonomous, just to make the work easy for the farmers, because the other prototypes, the ammonia trapping prototypes, were quite difficult for the farmers to work with. So these new models are more ergonomic and easy to handle for the farmers. We also have improved the efficiency of the system, just lowering the cost. That was the bottleneck of the technology. And we want to market the new models when the project finish, recognize the byproduct as a renewed product, and request the technology as a best available technology. So that's what we are working now, and we keep working because we have a lot of work to do too. So thank you so much for your attention, and thank you, the Beta Group, for inviting me. Thank you.
Thanks a lot, Maria Cruz. I liked a lot all the story. So it's a success story, I would say. It's fantastic to know how you started with this and at what point did you arrive. So I loved your presentation, and congratulations for all the milestones that you reached. And we hope to be able to see this technology in the market soon, and also as a new best available technique. So congratulations.
Thank you. Thank you so much.
So in this case, thank you to Tinka. We have a question in the chat, and she says, "Good afternoon. I was wondering how the farms were chosen. Are these representative farms, or which criteria did you use?"
The criteria for the second project, for the green ammonia, project, one of them we have been working with one of them in the ammonia trapping project. So they wanted to continue working in this new project, and this and the other farms that we have chosen, Agrocesa is part of one of the most important company in Spain that products meat, pig meat, that is Valcompagnes. So it's a part of this huge company, and they wanted to work with this project because the first farm has been talking to the second farm. And they wanted to share the technology. They wanted to be part of that technology because they have a huge problem with the ammonia. So the second farm, Agrocesa, wanted to be part of this project because the first farm were talking with them and wanted to be part of this project.
Fantastic. Thank you. Yes.
No,
go ahead.
That's all.
Okay. Thank you. So we have a second question. It's from Eva Brusselman, and she's asking, in which way is the technology better than the traditional air scrubbers?
We think it's better because of it works without any pressure and at ambient temperature. So we don't need to invest money, invest energy, with high pressure and high temperature, as it works with ambient temperature and no pressure. This membrane doesn't need pressure to work.
Perfect. Thank you very much. Is there any other question? Nagore raised her hand. So Nagore, please go ahead.
Yes. Thank Thank you very much, Maricruz. I joined LAIA because I found this presentation very, very good, and congratulations because you reached this TRL 9 almost, and this is something that it's not easy. My question goes regarding the composting process. Because you demonstrated in a closed system that this is also working very well to recover ammonia from this kind of process, which is raising the temperature naturally. But I wonder how we could somehow apply this, modifying the composter in a farm in which normally the piles are open.
Yes.
So how could be this adapted?
The composter that we have used in the ammonia trapping project was a closed composter, because we have been working previously with composting animal slaughterhouses and carcasses and all this kind of sandage products, and we use the composter for that. But if you want to translate the technology to an open pile, we are thinking about using a flat membrane. We haven't done any experiment, not yet, but we need to do that because it's another way to use the technology in an open system. But we think that a flat membrane will work better than the tubular membrane that we have been using now.
Okay, so if you decide to go on this research, I will be waiting.
Okay.
For the publication.
Okay.
Thank you.
Thank you.
Thank you. So if there's no more questions, so thanks again, Maria Cruz, for your presentation.
Thank you.
And now we move to the last presentation of today's webinar. The presentation will be made by Bart van de Castile, who is a senior researcher at ILVO. He's involved in projects on biochar use in Cascade, for example, applying biochar first to reduce emissions during biomass processing, and then use the biochar-enriched soil improvers for carbon sequestration. So the presentation that Bart will do is titled Biochar Amendment During Anaerobic Digestion and Manure Treatment for Mitigation of Gaseous Emissions, No Trade-offs when Products are Applied to the Soil. So Bart, the floor is yours.
Okay, thank you. You can go to the next slide, please. In this presentation, so I will explain a little bit about biochar use in Cascade and the topic of the trade-offs. And then we dive into the results of an experiment where we added biochar during manure processing. And then we go to sorption tests of ammonia and ammonium with biochar. And then we come to the last experiment where we added biochar in anaerobic digestion, and we added it also to digestate. And then we come to the conclusions. Next, please. This is a field at ILVO where we have applied biochar, and it's the picture is taken just before we have incorporated the biochar into the soil. And the research question we had as a soil scientist was, what is the added value of this biochar beyond carbon sequestration in the soil? Is there any added value for soil health or for soil dynamics for agricultural fields? So you can produce biochar and you can directly use it in the field, but there are also other options with biochar. So that's the next slide. So we know that like the best biochar for carbon sequestration, you make it out of woody biomass, woody feedstocks. And during this pyrolysis, so the conversion into biochar, you can also produce renewable energy. So this is very important that you have a good installation that also provides you with high quality biochar, but also with renewable energy. And this biochar you can or directly apply in the field for long-term carbon storage. But on the other hand, and that's the next, You can also use it for environmental applications. You can use the biochar as such, or you can optimize the biochar for doing this job. So you can use it for absorption of a lot of pollutants. You can use it to reduce ammonia emissions or greenhouse gas emissions. You can use it as a carrier for nutrients or microbiology. It can be a catalyst in a lot of processes. You can use it to optimize processes like composting or anaerobic digestion. You can even use it as a feed additive, and you can use it to grow plants on, so you can use it as a horticultural substrate. So there are a lot of applications for biochar, but of course the type of biochar is really determining for which kind of application you can use it, the better. And the next question is, of course, should we use all biochar to store carbon in the soil, or should we use all biochar for environmental applications? And this question brought us to the idea of the cascade use of biochar. So that's in the next slide. So here we tried to combine different applications. For instance, we took biochar and we used it in manure processing or in anaerobic digestion to optimize the processes to reduce the ammonia emissions there. And after that, we used these products, this manure or the digestate with the biochar in the field, in the soil, to see what is there, the effect on the soil quality, and also to see if there were no trade-off effects, for instance, that we had higher emissions if we had the products with the biochar used in the field. Next, please. So it's about the biochar and the soil. So when we talk about trade-offs, it can be considered as at two levels. It can be considered at the level of a process, because if you aim at reducing ammonia emissions, but you increase the N2O emissions or the methane emissions, it's not a good strategy maybe. But also when you have this cascade application and you have again in one step, you have lower ammonia emissions, but in the next step during soil application, you have higher ammonia emissions. It's also not really a good option to do this. So this is the topic of the presentation. And then we start with the first experiment. It was about cattle slurry storage. And we applied different types of biochars, and we combined it also with elemental sulfur or with clinophthalate. And in some of these treatments, we could really see that there was a quite clear reduction of the ammonia losses. So it was more than 10%. So this ammonia was like captured in the system. And then we did, in the second step, we did a separation of this slurry into a liquid and a solid fraction. And also with some biochars, we also saw a higher separation efficiency. So more material ended up in the solid fraction of the slurry. And then the last step was the most important for this research. We wanted to see if we applied the solid fraction with or without biochar in the soil, if we saw any differences in nitrogen releases or in nitrogen losses as ammonia. So this is the next step. So here you see the setup of the soil part of the experiment. So we mixed the solid fraction with the soil. We put it in closed containers. We put it at the standardized water content of the soil. It's the 50% water-filled pore space. We added the products at a similar nitrogen dose. It was a quite high dose to have really these kind of emissions that we could measure. These closed containers were then stored in a climatized system, and they were all connected with a semi-continuous gas analyzer, so we could continuously measure all emissions like ammonia, but also N2O, methane, CO2 from this system and compare the different treatments. Next, please. So we saw actually that for the products with the biochar, so the solid fraction with the biochar, we had, of course, more carbon input into the soil with the same amount of nitrogen, because biochar, it's like almost pure carbon. But we also saw that more nitrogen was organically bound, and it worked like a slow release fertilizer. Even more important was that the nitrogen, which was previously sorbed on the biochar in the solid fraction, it was not released as ammonia after soil application. And then when we made the nitrogen balance, we saw that more than 90% of the the total nitrogen that was released as nitrate, and only very minor amounts were released as ammonium or were lost as ammonia. So this was quite good news. And more information you can find in this publication. But then the next question, it's in the next slide, was of course, what kind of biochar is the better biochar to be used to sorb either ammonium or ammonia? So we did tests for sorption of a lot of different types of biochars. We were quite lucky to have different feedstocks converted into biochar at different temperatures and in different installations to make this exercise. So we had, on the one hand, a very simple sorption test to see what happens with the ammonium when biochar is exposed to ammonium. And on the other hand, we also measured the sorption of ammonia in a setup where a closed container with biochar was exposed to a gas flow with a known ammonia concentration, and it was connected to a multi-gas analyzer, and there we could monitor actually what happened with the ammonia in the gas, and how much of this ammonia was retained and was sorbed by the biochar. So, and at the end of this research, we were quite fascinated by the fact that actually nutrient-rich biochars and mainly manure-based biochars were the winning ones for the ammonium sorption. So they had the highest ammonium sorption. So mainly biochars with a high nutrient content and a high CEC, a cation exchange capacity, they had a high potential for ammonium sorption. And this is quite fascinating because, on the other hand, we also know from research that when you convert, for instance, the solid fraction of manure into biochar, it also works as a cleaning method. You get rid of a lot of contaminants or other issues like microplastics. They are removed. PFAS concentrations, they are strongly reduced. Antibiotics, they are also destroyed during this process. But it's also a way of getting rid of pathogens or antibiotic-resistant genes. So a lot of issues we normally have with manure, they can be reduced strongly by converting them into biochar. It also may have an added value in terms of nutrient balance, because during this process, nitrogen is converted into the gas phase of the process and can be further treated there, while the other nutrients and carbon, they are up concentrated in the biochar, so you get really another type of material in terms of nutrient content than you initially had in the manure. Next, please. So we also wanted to know actually what happened with the nitrogen that was sorbed as ammonia or as ammonium on the biochars. So we did a soil incubation trial with two types of biochar, so an insect frass biochar and a green waste biochar. And these two biochars were also treated with either ammonia or with ammonium. And then after 100 days, we looked how much of the total nitrogen was mineralized during these 100 days in the soil. And it was very strange to see that actually only the biochar treated with the ammonium released actually mineral nitrogen after 100 days. We expected that for the pure biochar, there would not be any nitrogen mineralization that was significantly different from the blank soil, because biochar is quite low in nitrogen and it is really low in mineral nitrogen. But for the biochars treated with the ammonia, we also saw that the sorbed ammonia was not released as mineral nitrogen after 100 days. So this is quite important to know, I think. Yeah, thank you. Next, please. So if you want to know more, you can read it all in this paper. And then we come to the last experiment of today. Here we wanted to see if we add biochar to the anaerobic digestion process, what happens actually with the process, but also with the digestate. So we had an experiment together with OWS. We had two control treatments, and then we had two reactors where one type of woody biochar was added and two reactors where frass biochar was added. And then for the control reactors, we took the digestate out of it And we then also mixed it with the 2 types of biochar, so we could compare the effect of adding biochar during versus after the process for these 2 types of biochar. Next, please. And also here, the digestate was mixed with soil in a closed container and with the same setup as we had for the manure storage experiment. And we also looked at the nitrogen release during 28 days in this closed system. Next, please. So maybe first focus on the anaerobic digestion process, because there we saw actually that the ammonia levels in the reactors, it decreased, which is quite good news, because too high ammonia levels, they can inhibit the digestion process. And we also saw that the ammonium levels were lower in this system because there was ammonium absorption taking place in these reactors on the biochar. So we didn't see a positive effect on the methane production, which was reported by others, but we saw a clear effect on the ammonia levels. When we added the biochar to the digestate after the process, we saw also a positive effect because, you of course increase the carbon content and also the value of the digestate as a soil improver. But the most important was actually when we applied the digestates to the soil, we didn't see any shifts in ammonia emissions or N2O emissions. And we also saw very low mineral nitrogen release. And because the biochar is very stable carbon, we also saw that the digestate with the biochar had lower CO2 emissions. So we had more stable carbon in the soil than without the biochar addition. So next slide, please. So for the anaerobic digestion, we saw no positive effect on methane yield, but a reduction in the ammonia formation and also ammonium sorption. We saw better properties of the digestate when biochar was added during or after the process. And then the soil application did not result in any trade-offs in terms of nitrogen emissions, and we had lower CO2 emissions, pointing at more stable carbon sources applied to the soil. More information you can find in this paper, and then we come to the overall conclusions. In all of these applications, of course, it's very important that we use quite low biochar doses. It's not, if you have already a lot of manure, it's not the intention to add a lot of biochar to this system. So low doses of biochar should already have a significant effect, as we could see in some of the treatments we did. When you apply biochar during manure storage, there is a potential of reducing the ammonia emissions. And this ammonia is not released when you apply the products in the soil, which is quite good news. We also saw that nutrient-rich biochars have a higher ammonium sorption capacity. When nitrogen is sorbed as ammonia, it's not released in the short term after soil application, while when it's sorbed as ammonium, it's slow released after soil application. And then for the anaerobic digestion, we saw a higher ammonium sorption and no risk for trade-offs in terms of ammonia release in the soil. And maybe very important is in all of these applications that you only can use biochar once for reducing the ammonia emissions or the greenhouse gas emissions. But afterwards, these products with the biochar you still can use for other applications, including long-term carbon storage and improving soil health and agricultural fields. So next, please. So yeah, you can go through. Yes. Well, in this graph, we saw that for different types of biochar, some biochars are very rich in carbon, like the woody ones, or some are very rich in nutrients, like the manure-based biochars. And it's very depending on what kind of applications you want to use these biochars for, that you need a certain type of feedstock and a certain type of process. So this knowledge is very important to come to targeted applications of biochar in agriculture. So thank you for this, for your attention.
Thank you very much, Bart, for your presentation. So I think that, yeah, we had 3 different approaches today for mitigating the emissions. So I think that it has been very interesting to see all of them. So thank you very much also for participating. So is there any question for Bart or, yeah, for any of the speakers? Because we are reaching, let's say, the end of the webinar. So if you have any comments, questions, you can put them in the chat or raise your hand. No questions, no comments. No. Thank you very much, Bart. Yes, Elio. Elio, please, you can, yeah, please go ahead.
Yes, thank you. Yes, I have just a question for Bart. Yes, I'm wondering to know, to have some information, if possible, about the temperature parameter of the gasification process that you used to produce biochar from frass or wood material. Because the temperature is an important parameter that influence the properties of biochar.
Yeah, you're right. But we were quite lucky that we had some feedstocks. They were processed at 400 degrees, some at 650, and some at 750. And for instance, for the ammonia sorption or the ammonium sorption, the temperature was not really that important. It was more like the feedstock that was very important. But on the other hand, if you increase the temperature of the biochar production, you also increase the nutrient content. You get more concentrated products, and you have a higher CEC. So it also indirectly affects the ammonium sorption of these biochars. So the temperature is also important, but for some applications, it's mainly the feedstock that is determining how you can apply it. Okay.
Just another question, but according to your experience, so because if you understood well that the temperature is important, but not so important. So generally, biochar in some pyrolysis plants in Italy is produced by using around 800 to 900 Celsius degrees. Do you, according to your experience, is it good temperature or is too much?
I think it's very high, but yeah, I don't think we have tested biochars produced at that high temperatures. I think 750 it was like the upper limit. Well, what you have actually, if you produce biochars at like 500 degrees, which is already quite hot, you still have some active carbon or reactive carbon. While if you go beyond 650 or 700, you only have very stable carbon in your biochars. So for some applications, you still need this small label fraction of biochar to start some of the processes, I think. So yeah, if you go really at very high temperatures, you get like, it's like fossil carbon, let's say that's not reactive maybe anymore. I don't know.
Yes, thank you. Thank you very much.
Thank you very much, Elio, Bart. Yeah, so I think that now it's time to close the webinar. So first of all, a big thank you for the 4 speakers that we had today, Diogo, Elio, Maria Cruz, and Bart. It has been a pleasure to have you here and to hear your experiences. So thank you very much for your willingness to participate. Thank you also for all the people who attended today's webinar and also the webinar that we had last week about this topic. We hope that the topics that were tackled were of interest. So we will continue working on that topic and other that could be relevant for the projects that are part of the ESNI community. Just as a quick wrap up before closing, just to remind what ESNI is aiming to do. So at the end, as I was saying at the beginning, ESNI is willing to put together projects that are working in the field of nutrient recycling. So in this regard, we are bringing projects together to identify topics that could be of interest. Then based on that, organize topic-focused webinars like the two that we organized this time about the emissions. We are also willing to organize joint activities and initiatives between projects. So this means that if projects has to organize joint events, that we can support them on doing that. Also to do joint publication, joint position papers, joint proposals for future projects, etc. Then you are also welcome to share with us some news that you would like that ESNI can publish in the web page bulletin, so we can help you on spreading and disseminating your news, the news of your projects. And at the end, we also like to contribute to different ongoing conferences and events that are taking place. And I just didn't went to the first one, which is the annual event ESNI conference, because there's some news that we wanted to share with you, and is that since this next year, ESNI and the European Sustainable Phosphorus Platform have been joining forces to organize together what we call the ESNI NERM conference. So we are merging the ESNI conference with the conference that the ESPP organized in the past related to nutrients in Europe research meetings. So let's say the research-oriented conference of ESPP. So we will have the first edition of ESNI NERM next April, April next year, sorry. So the 28th and 29th of April of 2026 in Brussels. So the dates are already fixed. And in this case, if some of your projects are interested in organizing a workshop in this conference, or you are willing to participate, so please feel free to contact us, because now we will start building the conference program. And that's all from my side. So again, thanks a lot to the speakers and all the audience. And I wish you all a very nice afternoon. See you soon. Thanks a lot.
Thank you.
Thank you. Thanks a lot. Bye.
Thank you very much.
Bye-bye.
Bye.
Thank you.
Bye.
Thanks. Bye-bye.
Bye.
Bye.